A lot of the work that we do here at Alden is to reduce the pressure losses through power plant components. But one of the issues with a wet stack is the fact that you can't put any turning vanes in without the potential for re-entrainment back into the gas flow. So in discussions with HADEC, who we've done many, many projects with, we decided that this was a really good area for a joint cooperation to try to develop a turning vane that could operate in a wet environment, because it'll have massive advantages for the power plants that implement it. Now, in the testing that we've done, we've been able to reduce the pressure loss coefficient of the bottom of the stack by almost 70%, which is going to result in a massive reduction in the pressure losses through the system. But there are some additional advantages. One of the main ones is if there is any liquid re-entrained within the gas flow, they will deposit on these vanes, and we can remove that from the gas flow before it exits the top of the stack. So the project was divided into two phases, in two models. The first phase was a model that was used to develop the actual design of the turning vanes themselves. And to do that, the model included 3 vanes. It looked at the aerodynamics of the system. We used smoke to look at flow visualization to see what the flow patterns were through the system. We took pressure loss measurements and velocity measurements to look at the flow profiles and the reduction in pressure losses.
Well, in this model, we're trying to minimize the pressure loss as you go from a rectangular turn 90 degrees up into a round stack. So the vane is thicker in the middle, so it's like an airfoil for an airplane, and what happens is the gas doesn't separate as it goes around there. It stays attached to the vane. You probably could see that very well with the smoke.
Right.
That the smoke just has a nice even line. The streamlines are very smooth going through this turn.
What's really nice about this is now the location of the SEMS metering system doesn't necessarily have to be way up high anymore, because we used to you have to put them up because you have a lot of rotation in the gas.
Right.
But this is going to have no rotation.
The second model was a model looking at a single vane to develop the liquid collection capability of that vane. And the reason we had to use only one model is because we use actual water, and that water doesn't realize it's in a flow model, so it's going to create droplets and re-entrainment just the same as it would in the actual unit. So we can't really do that with 3 vanes. It would not be an accurate representation. By doing it with one vane, we can design the liquid collection aspects accurately.
Liquid will impact this turning vane. At the lower level, it's going to start to go up, but then it kind of stagnates. So we put a V collector in there to direct it out to the side of the breech where we can get it out of the system. Then about 2/3 of the way up, the liquid flows down. That liquid we collect behind the V when there's a drain there to drain it internally inside the vane. At the top of the vane, we have a scoop, so any liquid that's going up goes inside that scoop and flips down inside the vane as well. And all this liquid is collected internally to the vane, and then we can take it and direct it out to the sidewalls where we can drain it externally, or we can drain it internally down to the base of the stack.
Any plant that uses a wet stack could retrofit these types of turning vanes in and get a significant reduction in pressure losses through their system. For a 500 megawatt plant in the United States, that equates to a little bit over 1 inch of water in pressure reduction, and that equates to somewhere in the neighborhood of $1 million a year of operating costs.